Good morning. Today's chapter is solvent extraction. General discussion. Liquid extraction is the technique in which a solution, usually aqueous, is brought into contact with the second solvent, usually organic, essentially immiscible with the first, in order to bring about a transfer of one or more solutes into the second solvent. The separation that can be performed are solutes into the second solvent. The separation that can be performed are simple, clean, rapid, and convenient. In many cases, separation may be effected by shaking in a separatory funnel for a few minutes. The technique is equally applicable to trace levels and large amounts of materials. In the case of inorganic solutes, we are concerned largely with the samples in aqueous solution so that it is necessary to produce substances such as neutral metal chelates and non-association complexes which are capable of extraction into organic solvents. For organic solutes, however, the extraction system may sometimes involve two immiscible organic solvents rather than the aqueous organic type of extraction. The technique of liquid extraction has of course been widely used to separate the components of organic system. In particular, solvent extraction may be employed to effect a cleanup and to achieve concentration of the solute of interest prior to analysis. This is illustrated by the cleanup steps which have been used for the analysis of organochlorine pesticides at the zero point 0.1 UZZ-1 level in animal fats and dairy products. In one such procedure, the solution of animal fat in hexane 25 ml is extracted with three successive portions 10 ml of dimethyl formamide DMF saturated with hexane. The combined DMF extracts are washed with hexane 10 ml saturated with DMF to remove any remaining traces of fat. After separation of the hexane, it is equilibrated with further DMF 10 ml to reduce loss of pesticides residue. The pesticide compounds are finally part, partitioned back into clean hexane after adding water to the combined DMF extracts. The hexane layer is used for the quantitative analysis of the extracted pesticide residue using gas chromatography with an electron capture detector. Section 9.24. It is of interest to note that the extraction procedure involves two organic phases such that no aqueous phase is involved and that immiscibility is minimized by saturating each solvent with the other. Extraction procedures for organic species, however, do not in general possesses the same degree of selectivity as may be achieved for metal containing system, and the chief analytical application of solvent extraction is for the determination of metals as minor and trace constituents in various inorganic and organic materials. Although solvent extraction has been used predominantly for the isolation and pre concentration of a single chemical species prior to its determination. It may also be applied to the extraction of groups of metal or classes of organic compounds prior to their determination by technique such as atomic absorption or chromatography. To understand the fundamental principles of extraction, the various terms used for expressing the effectiveness of a separation must first be considered. For a solute A distributed between two immiscible phases A and B, the Nernst distribution or partition law states that provided its molecular state is the same in both liquid and that the temperature is constant. Concentration of solute in solvent A divided by concentration of solute in solvent B equal to concentration of A by concentration of B equal to Kd, where Kd is a constant known as the distribution of partition coefficient. The law as stated is not thermodynamically rigorous. Example, it takes no account of the activities of the various species and for this reason would be expected to apply only in very dilute solutions where the ratio of the activities approaches unity. but is a useful approximation. The law in its simple form does not apply when the distributing species undergo dissociation or association in either phase. In the practical application of solvent extraction, we are interested primarily in the fraction of the total solute in one or other phase, quite regardless of its mode of dissociation, association, or interaction with other dissolved species. It is convenient to introduce the term distribution ratio D, extraction coefficient E, D equal to Ca bracket A by C of A bracket B, where the symbol Ca denotes the concentration of A in all its form as determined analytically. A problem often encountered in practice is to be determine what is the most efficient method for removing a substance quantitatively from solution. It can be shown that if Vml of say an aqueous solution containing X naught gram of a solute be extracted n times with Vml portions of a given solvent, then the weight of solute Xn remaining in the water layer is given by the expression Xn equal to X naught bracket dv by me dv plus v की power n, where d is the distribution ratio between water and the given solvent. It follows therefore that the best method of extraction with the given volume of extracting liquid is to employ the liquid in several portions rather than to utilize the whole quantity in a single extraction. This may be illustrated by the following example. Suppose that 50 ml of water containing 0.1 gram of iodine are shaken with 25 ml of carbon tetrachloride. The distribution coefficient of iodine between water and carbon tetrachloride at the ordinary laboratory temperature is 1 by 85, such that at equilibrium the iodine concentration in the aqueous layer is 1 by 85th of that in the carbon tetrachloride layer. The weight of iodine remaining in the aqueous layer after one extraction with 25 ml and also after 3 extraction with 8.33 ml of the solvent can be calculated by application of the above formula. In the first case, if x1 gram of iodine remains in the 50 ml of water, its concentration is x1 by 50 gram ml inverse. The concentration in the carbon tetrachloride layer will be 0.1 minus x1 divided by 25 gram ml inverse. Hence, x1 divided by 50 divided by 0.1 minus of x1 divided by 25 equal to 1 by 85, या x1 equal to 0.00230 gram. The concentration in the aqueous layer after 3 extractions with 8.33 ml of carbon tetrachloride is given by x3 equal to 0.1 bracket 1 by 85 into 50 divided by 50 by 85 bracket plus 8.33 whole power 3 equal to 0.000287 gram. The extraction may therefore be regarded as virtually complete. If we confine our attention to the distribution of a solute A between water and an organic solvent, we may write the percentage extraction E percentage as A percent is equal to 100 concentration of A naught V naught divided by concentration of A naught V naught plus concentration of W V W equal to 100 divided by D plus VW divided by V naught bracket 1, where V naught and VW represent the volume of the organic and aqueous phase respectively. Thus, the percentage of extraction varies with the volume ratio of the two phases and the distribution coefficient. If the solution contains two solutes A and B, it often happens that under the condition favoring the complete extraction of A, some B is extracted as well. The effectiveness of separation increases with the magnitude of the separation coefficient or factor beta, which is related to the individual distribution ratio as follows: beta equal to concentration of A naught divided by concentration of B naught divided by concentration of AW by B concentration of B W equal to concentration of A naught divided by concentration of AW divided by concentration of B naught divided by concentration of BW equal to dA by dB. If dA equal to 10 and dB equal to 0.1, a single extraction will remove 90.9% of A and 9.1% of B ratios 10:1. A second extraction of the same aqueous phase will bring the total amount of A extracted up to 99.2% but increases that of B to 17.4%, ratio 5.7 ratio 1. More complete extraction of A thus involves an increased contamination by B. Clearly, when one of the distribution ratio is relatively large and the other very small, almost complete separation can be quickly and easily achieved. If the separation factor is large but the smaller distribution ratio is of sufficient magnitude that extraction of both components occur, it is necessary to resort to special techniques to suppress the extraction of the unwanted component.